Hey guys, hope everybody's doing well. I have a bit of a cold, just a heads up. Shouldn't be an issue, but just so you know. Okay, today we are going to talk about correlation and covariance. These are numerical summary measures, so we're still kind of in the intro section to statistics, but these are when we start to really scratch the surface of some of the real power of statistics. If you're following my videos, if you're watching this is because you're trying to brush up on stuff, you might be jumping right to that stuff. If you're following my videos or taking my class, then it's going to be a little while before, maybe a long while before we get to the really powerful stuff. But this really is very commonly used. In particular, correlation is very commonly used because this captures the relationship between two variables, right? In particular, it captures the linear relationship between two variables. But lots of things we can use linear approximation to try to capture how they move together. Not two variances, two variables. Now we need to know all sorts of stuff about one variable before we get here. And so we learned about the sample mean, x bar, right? We learned about the sample variance, s squared, and the sample standard deviation, s. And these are really useful to capture and describe one variable. And this is one way we can use them. Once we know how to calculate a sample mean and a sample standard deviation, and a sample variance, we can take that knowledge and use it to measure and quantify the linear association between two variables. This comes in handy literally all of the time because relationships is really what we're looking for in the world, right? The world is connected, and when we want to try to understand things, one way that we try to understand them is by looking at one thing that we know something about and using that to make predictions or inferences, guesses about something we don't know something about, just to gain insight, right? Relationships between two variables, that's huge. Should I go to college? Well, it depends. Will it mean you make more money? In that case, how are education and income related? Right. So that's one thing, right? Should I boost my advertising? Well, that depends. How does advertising affect sales? If we can understand this relationship, then we can say something about what your next course of action should be in some related area. So I'm going to work from an example here. In this case, we have a very small data set. In real life, this data set would be much larger. As it stands, we kind of want to have something while we're learning that we can wrap our heads around. So here I have 7 customers. Each of them has bought some food at a restaurant called Oleander. I don't know, I just made it up. There you go. They have an age. They each bought a meal. They had a price, and then they put their satisfaction on a scale from 0, which is completely unsatisfied, to 10, completely satisfied. So, you know, this restaurant is doing okay. But what they would really like to know is, how are price and satisfaction related? So in this case, the relationship they care about is the relationship of price and customer satisfaction. Now, why would they want to know that? Well, for one thing, if the expensive dishes are highly satisfying, then maybe they should raise the price or lower the portion size, right? They can maybe make a little bit more money. Maybe they're undercharging. On the other hand, if the cheap dishes are very satisfying, that tells them something about their customers. Their customers want cheaper food, or the cheap food is really good. And so they could either raise the price of that, maybe they could swap things around. In this case, it looks like all the expensive dishes are seafood dishes, $11.75, $11.75, and $12. And so maybe they just, these are very satisfying, and it looks like people are satisfied, maybe they can say we have really good fish. And so in the marketing strategy, they might want to advertise that. And so we're going to try to take advantage of that. Now, let's say we did give them some advice, and then they changed things, and this relationship adjusted. Well, if we can quantify this relationship, then we can say something about what to expect in the future, or whether things have changed in one direction or the other. So in order to kind of visualize this, one thing we often like to use is a scatter diagram. And so here I have a scatter diagram. I have price on the horizontal axis and satisfaction on the vertical axis, and I've added these 2 red lines at the I already calculated the sample mean, price and sample mean level of satisfaction, just to give us something to look at and talk about. And what we can see here is that we have 7 data points, 1, 2, 3, 4, 5, 6, 7, and we have a lot down here in this lower left quadrant and some up here in the upper right quadrant. We have none in the lower right and only 1 in the upper left. And so it looks like what we have is something where at lower prices we have lower levels of satisfaction, and then as we go up at higher prices we have higher levels of satisfaction. And it's not perfect, right? We have dots around here, but it looks like generally we have an upward sloping relationship. This is called a positive relationship, partly because we're going to get a positive number later. We would expect to have a covariance and a correlation that are positive. Again, though, I mean, if we had different dots in different places, it would change this relationship and the level of associatedness in a way that we would like to be able to quantify. And so, one way we are going to the first way we are going to quantify this is with what is called the covariance. In particular, it is going to be the sample covariance of x and y. What we want to do now is we want to look at how x varies and how y varies, and then whether they move in the same direction or move in opposite directions. We want to quantify that. So we're going to use a formula that's going to come up with a number. So the sample covariance of x and y is s sub xy. These are subscripts. And then to calculate this, it's going to be a big fraction. And it should look a little bit like the sample variance formula, except instead of taking the deviation in x and squaring it, what we're going to do is we're going to take the sum from I equals 1 to n of xi minus x bar. It's xi minus x bar times yi minus y bar all over n minus 1. So let's break this into pieces. So xi, that's going to be the value of x for observation I. And then you may previously have seen x bar just defined as the sample mean. So let's just call it that for this moment. So that's the sample mean. Yi is the value of y for observation I. And then y bar, well, that's also a sample mean, and this is where we have a little bit of a problem. Not a huge problem, but if we want to be precise and specific, we don't want to call these both sample means, right? We want x bar to be the sample mean value of x, right? And y bar to be the sample mean value of y. Now, when we measure these, right, what we have is we have the deviation in x, right, for observation I, the deviation in y for observation I. We're going to multiply those together. Once we do all that, then our summation symbol, right, we've seen this big sigma a lot of times now. The summation symbol tells us once we get those products to sum those products, and then to divide by n minus 1, and n is our sample size, right? It's the number of observations we have. Cool. So that's what we're going to do. Now, it's useful to just look at this formula and think about it for a little while, right? Now, if we call price x and satisfaction y, then an expensive meal is going to have an xi greater than average, right? That's why we call it expensive. Relative to the rest, it's expensive. And so if we have an expensive meal, that means that xi minus x bar is going to be greater than 0, right? That's going to be positive. Now, there are two possibilities as far as satisfaction are concerned, right? Two major possibilities, right? One is it's unsatisfying. If it's unsatisfying, then yi is going to be less than y bar. That means that yi minus y bar is going to be negative, right? And then if we multiply them together, as it tells us to do in this formula, we're going to have a positive times a negative, and that will give us a negative number. Right? On the other hand, if they're more satisfying, and in this case it seems like they are, then this should be positive, and when we multiply them together, we should get a positive number. Similarly, if cheap meals are less satisfying, then xi minus x bar should be negative, and yi minus y bar should be negative, and a negative times a negative is a positive. And so if we have a positive relationship, meaning that higher price leads to higher satisfaction, the higher price meal should yield a positive result here, and the lower price meal should also yield a positive, and then we add up positive numbers, we should get a big positive number on top, right? That's what we would expect. Alternatively, if we had a negative relationship, then these would be have opposite signs in general. And when you multiply things with opposite signs, you get a negative number. You add up a bunch of negative numbers, you get a negative number. And so we can look at this formula and just by taking a look, kind of see what predictions we might find. Okay, well now let's walk through the formula. In order to do this, let me create some new columns here. First, I'm going to need to get x bar, and I have a little data range over here. My x bar is going to be my average value of my x's, right? So the average of these numbers, $11, as is indicated right here. I already calculated this, right? My average satisfaction level is 8.00. Right? That's by design. I made up this data, but it's pretty straightforward. Okay, now I need to calculate the numerator. Well, that's going to take a little bit of work, but we can do it. The first thing we want to calculate is xi minus x bar. And so we're going to have 12 minus 11. And then I'm going to want to subtract this 11 every time. So hit hit F4, make that absolute reference. And now when I copy it and paste it over and over again, you can see that we have these positives, which are in the black, and then the negatives are in parentheses and in red. And sure enough, $11.75 is 75 cents more than $11, and $10.50 is 50 cents less than $11. Now, I don't want to add these up yet. The summation symbol over there, I don't want to add these up yet because if I do add them up, I'll just get 0. That's what that says right there. The sum is 0. So I don't want to do that. What I do want to do is find the y deviation. So yi minus y bar. Here's my yi, satisfaction score. And I want to subtract my average satisfaction score. That's this I-25. Hit F4 to make that absolute. And 10 is 2 more than 8. 0, negative 2, 1, 1, negative 1, negative 1. Right? So those are my yi minus y bars. Okay. You can see that in general, if this is positive, this is likely to be positive or 0. If this is negative, well, 3 out of the 4 times the negative number on the left corresponds with the negative number on the right. Here's one where it doesn't, but in general, it looks like what we have is a positive relationship. Now what we have to do, the formula tells us, is to take the product, right? Xi minus x bar times y minus y bar. I'm going to call this x dev times y dev for x deviation times y deviation. And you get 1 times 2. 0 times anything is 0, all the way down. And those are my products. Okay. Now here you see that these are almost all non-negative. There's only one negative number. And so when we add these up, we should expect to get a positive number. And that sum is going to be my numerator. Right? Because I have all the products, we add these up for I equals 1 to n, and 4.5 is my numerator. Now I need to divide by n minus 1. So what's n? Well, n is the number of observations that I have. You can use the count formula to get those, or I could just count. It's 7. My denominator is going to be that minus 1. Oops. There we go. And now, to finish the formula, I take my numerator, divide by my denominator, and 0.75 is my sample covariance for this. So here we go. S sub xy equals 0. That's a y. 0.75. Now, is that a large sample covariance or a small sample covariance? I'm not even sure what that means, really. What we can say is that this is greater than 0. And it's useful. It captures something of the relationship between these two values, which is nice. It's positive, and it would be a good predictor of the covariance in the population. If we want, oops, a daisy. If we wanted to calculate the covariance in the population, we can do that. Or we could at least specify what it is. That's going to be sigma sub xy equals the sum of xi minus mu x times yi minus mu y all over big N. And you can see that they're pretty similar, right? Sigma xy is the true population covariance. Mu is the true population mean for x and y, and then n is the true population size. We don't have to make the sample adjustment by subtracting 1 here. This is a y, by the way. But we can't do this, unfortunately, right? We can't actually calculate this because this is too big, n is too big. That's the whole purpose of statistics. The whole reason for its existence is that the population is just too large. But we can specify what it is. And it'll give us a relationship, right? And that's what SXY is really trying to get. S sub XY is really trying to get to. Our sample covariance is trying to capture that. The problem with covariance, this is true for both the sample and the population covariance, is that it depends on the unit that we use to measure it, right? We measured the price in dollars, but if we measure this in cents, 1,200, 11, oopsie daisy. Let's just say this is 1,200, 1175, 1075, 1050, 1175, 1050, 975, right? Now let's say these instead, it looks like it's in dollars, but you can just imagine these are cents because that's what it would be. Well, now we can see that S sub xy is 75, right? It's still positive. It shouldn't change the sign if we change the units, but it does change the value. And so is 0.75 big or large or small? Well, it really depends on whether you measured in cents or whether you measured in dollars. Similarly, if we change these satisfaction scores to a scale of 1 to 5, 5, 4, 3, 4.5, 4.5, 3.5, 3.5, now that's, we have the same variation in satisfaction. They're each exactly half of the original size, and our covariance has reduced by a factor of 2. We don't really want that to be the case. We don't want the units we measure in to change our measure of the relationship between these two variables. The reason is that really what we want to do is capture how much we can learn about one thing from the other thing in general. I mean, S sub xy is handy. But if we have exchange rates involved, or we have different scales of satisfaction, then we can't really compare apples to apples. What we would like to do is to find some sort of scale-independent measure of relatedness. So we're interested in scale independence. And if we can find a measure of scale that's scale-independent, a measure of relatedness, that would be really handy because we could use it to compare the relationship or the amount of relationship between any two data sets. Fortunately, there is one. It's called the Pearson Productmoment correlation coefficient. Generally, we just call it the correlation coefficient. And it's one of the most important. I would put this up there with sample mean and sample standard deviation as like the third one that I see the most often, or that I use the most often to try to learn something. The symbol we use for the sample correlation coefficient is R sub xy. And the formula for it is S sub xy divided by S sub x times S sub y. It's easy to calculate once we know our sample standard deviation, our sample covariance, and our sample variances. So what do we have here? Let's pick a different color. Well, S sub xy we just found, right? That's our sample covariance. But we've never seen an x or a y with a subscript before, with just a single subscript. So S sub x, well, that's going to be our sample standard deviation. And S sub y is also going to be our sample standard deviation. But in this case, this is of x, and this is of y. And this has a very satisfying interpretation. I like it. This bottom is kind of like the total, some measure of the total variation in x and y, or total covariation, or the total variation between the two of them. And this right here is a measure of their variation together. And so the largest s sub xy could be in magnitude would be exactly equal to s sub x s sub y times s sub y. What that means is that the maximum value that rxy could take is 1. And if it were to take a value of 1, what we would have is a positive straight line that had a bunch of dots along it. They need not be evenly spaced. They just have to all fall on exactly the same line. And if I was better at drawing, that would be obvious that that's what these are doing. And this is rxy equals 1. The least value it could take, because s sub xy has a sign. If you remember from the formulas for s sub x and s sub y, which we covered back when we talked about variance and standard deviation, they have to be positive, right? Because it's the square root of the average sum of squared deviations, right? So you're going to take a sum of squared things, all of which are positive, divide it by a positive number, and then take the square root, which will also be positive. And so in the bottom here, we have a positive times a positive. But we just showed above that s sub xy can be negative. Now the largest negative it could be is exactly the same size as sx times xy, which means the minimum possible value of the sample correlation coefficient is -1. Okay. Now, if we had a sample correlation coefficient of -1, what we would have is x and y, a downward sloping line. Doesn't matter what the slope is, it just would have to be downward. That's straight, and all the points fall exactly along it. They don't have to be evenly spaced, and that looks fat, but it should be skinny. And this would be rxy equals -1. And so those are the two extreme cases for a sample correlation coefficient. We have names for them. Right? Both of these are perfect correlation, but on the left side we have perfect negative correlation, and on the other side we have perfect positive correlation. And in real life you don't see these unless you accidentally have two things that measure the same amount, right? So if you had GDP on one side and you had C plus I plus G plus net exports on the other side, that sum, like those are the same thing by definition. And so if you tried to find the correlation between those, you'd get a perfect correlation. And that would be an indication that maybe you did something wrong. Sometimes when you get to more advanced statistics, you accidentally have a variable that is a combination of other variables and you correlate them, and it's not good. All right. What about less than perfect correlations? Well, we might have a negative correlation that's more of a downward sloping kind of cloud, right? And this would be rxy is negative, but it's greater than -1, right? You draw a line through this, a linear association. It's going to be downward sloping, probably not that one exactly, maybe more like this. But it's not going to touch all the points. There's still going to be some variation there. Similarly, we might have correlation that's positive, that's just kind of a cloud of points that are generally in the upward direction. And so this would be rxy is positive, but less than 1. And then we have cases where we have no linear relationship. And there are some weird cases here. Now, no relationship at all is one of these, right, where you just have a star field. There's no relationship here. And so this is rxy equals 0, right? But you might also, if you're not careful, you can accidentally, and this is why scatter plots are so useful to kind of visualize your data, have a relationship that looks like this, right? Now this is going to have no linear relationship, right? The slope of this is going to be 0. So rxy is going to be 0. But clearly there is a relationship here, right? In this case, the relationship is just quadratic. It goes like that, right? And so we don't want to say there's no relationship, but we can confidently say, or measure it, that there's no linear relationship, right? And if you go to Wikipedia and look at correlations, there's a bunch of other cool graphs of things that have rxy equals 0, but clearly there is a relationship, or there's some pattern that underlies that. Okay, so for our data that we're dealing with, what is our correlation? Let's go back up here to the formula. You can scroll, there we go. What is our sample correlation coefficient? Well, in order to calculate that, we need to find our standard deviation. The short way, which I'm going to use because we're running kind of long on this video, is to use the stdev.s formula. That's the sample standard deviation formula. Oops. And I want it to be Actually, there we go. For my prices. 0.84 is my sample standard deviation for my y's. Sample standard deviation for my x's. For my y's should be 1.414 if I did this correctly, because I've done it a few times. And so that's my two sample standard deviations. To get the denominator for the correlation coefficient, I multiply these together, 1.19, and now I take my sample variance and divide it by 1.19, and positive 0.630 is what I get for my sample correlation coefficient. Cool. So which of these does that look like? It looks like this one right here, right? Something like that. It falls between those two, which is to say it's positively correlated. I would say it's moderately strong. And so usually what we talk about with correlation is the direction and the strength. Right? And so it's positively correlated and kind of strong, 0.63, right? RXY. Now this is my sample correlation coefficient. What we really care about clearly is not just the correlation for these customers. We want to know for all my customers what would that be. And to do that we use the Greek letter rho. Greek letter rho looks kind of like a P with no top, no thing up here. And in that case it's going to be my sample covariance, or my population covariance, sigma xy, divided by the product of my population standard deviations. Again, can't figure this out, can't figure these out, generally speaking, and so we use RXY to try to estimate that. But this is what we really are looking for. So what does this mean? Well, 0.63, that's positive. That means that when we have a higher price, we have a higher satisfaction score on average, and when we have a lower price, we have a lower satisfaction score on average. So what does that mean? Does that mean that people like spending money? Or does that mean people who are generally satisfied, right? If they're just happy, they feel good about life, they're going to like the food, and they're going to spend more on lunch, because when you're in a good mood, that's what you do. There's no way to tell that from this, right? That's one of the problems with observational data. And it's one of the fundamental problems of statistics, is that just because we have a correlation does not mean that there's causation in one direction or the other. It's hard to know which direction it goes. With experiments, you can try to pin it down. But certainly, we can say they tend to move together, and we can try to take action based on that understanding. So that's covariance and correlation. It's the last of our numerical summary measures that we're going to go over. And it's some powerful stuff. We use it kind of a lot when we're trying to suss out what's going on with a data set. Hope you guys found that useful. If you have any questions, as always, let me know, and I'll be happy to help. Thanks. Bye.